Good afternoon, and thank you for joining us for the 40th webinar in our Offshore Wind series, Learning from the Experts. I am Cheryl Huber, Senior Project Manager with NYSERDA's Offshore Wind team, and it is my pleasure to be joined by today's expert, Tricia Pellerin with Tetra Tech. Before I introduce Tricia, a few reminders for participants and some background on this webinar series. Next slide, please. Firstly, if you are experiencing any technical issues, please contact Sal Graven at the email address on the bottom of this slide. This webinar is being recorded, and the recordings and presentation slides for all webinars in the Learning from the Experts series are available on NYSERDA's website at the address on this slide. All participants have been muted. We will have time for Q&A following the presentation, so please use the Q&A function to submit your questions for the speaker. Use the All Panelists drop-down to ensure the NYSERDA team receives your question. Next slide, please. New York State is working to advance the responsible and cost-effective development of at least 9,000 megawatts of offshore wind by 2035. Offshore wind is a critical component in achieving the state's goals of 70% renewable sources of electricity by 2030 and 100% zero emissions electricity by 2040. While offshore wind has been providing clean energy to other parts of the world for several decades, this industry is brand new to New Yorkers. To provide interested stakeholders and members of the public with accessible, impartial information and opportunities for engagement on specific topics of interest, NYSERDA is hosting this educational webinar series called Learning from the Experts to connect the public with independent experts in key topics in offshore wind. We endeavor to select learning from the expert speakers based on their expertise, not necessarily for an alignment of opinions with NYSERDA or the state of New York. If you would like to suggest a topic or speaker for a future webinar, you can email us at offshorewind@nyserda.ny.gov or fill out a survey also available on our website, nyserda.ny.gov/OSW-webinar-series. Please note that the views and opinions expressed in this presentation are those of the presenter. Next slide, please. It is now my pleasure to introduce Tricia Pellerin. Tricia is a senior acoustic engineer and acoustics group lead at Tetra Tech with over 18 years of experience in environmental consulting. She has extensive experience in conducting acoustic monitoring, modeling analyses, and performing regulatory compliance determinations for a wide variety of projects throughout the United States, Canada, and internationally. Tricia's primary focus has been in the renewable energy sector, and she supports permitting of offshore wind energy development through the evaluation of in-air and underwater sound emissions associated with construction and operations. Thank you, and now I will turn things over to our speaker.
Great, thank you so much. Great. Well, yes, thank you very much for that great introduction, and for everyone on the phone that's joining to hear about the presentation today. So this afternoon, we're going to be speaking on in-air acoustic assessments for offshore wind. Next slide. So I guess Cheryl gave a really good introduction, but yes, I am Tricia Pellerin, the acoustics team lead at Tetra Tech. I'm located in Boston, and while my background is in biochemical engineering, I have had about 19 years of experience in environmental consulting, specializing in acoustics. Really, our team involves ourselves in all areas of acoustics, but certainly our focus has been in renewable energy, and especially offshore wind energy. We do work in both the underwater and in-air environments. Next slide. So today I'm just going to give a brief agenda of what we'll be discussing today. To start off, I'm just going to provide a bit of an overview on some acoustic metrics and terminology, followed by a discussion on noise regulations, and then kind of focus in a bit more on noise regulations in New York. provide some discussion on project activities that we look at in our acoustic assessments during construction and operation. Kind of address why maybe we might address some activities in a qualitative versus quantitative manner. Discuss ambient sound measurements, acoustic modeling, compliance assessment, review of noise mitigation measures if they're needed, and final design considerations. Next slide. So offshore wind energy acoustic analysis requirements. Why are these needed? Well, certainly acoustic analyses are included as part of the construction and operations plan, the COP, that lessees or offshore wind developers are required to submit to the Bureau of Ocean Energy Management, or BOEM, for their review and approval. And they really do involve two components, both underwater and in-air acoustic analysis. So for underwater acoustic analysis, we're really focusing on predicting potential noise impacts to marine species due to both construction and operation, especially activities like construction, such as pile driving. And we usually evaluate those impacts relative to criteria given by NOAA fisheries. Now, for in-air acoustic analysis, which of course is what we're speaking about today, we're modeling and predicting noise impacts really to human receptors due to both construction and operation. And we evaluate those impacts relative to a variety of different regulations at the state, county, and local levels. Next slide. So just as I said, I'm going to provide a bit of an overview on acoustic metrics and terminology to hopefully frame our discussion as we progress. So sound, what is sound? I mean, that's probably to some pretty obvious, but it is a vibration that propagates as a wave through a medium like air or water. Now, noise is really just sound with the further properties of being referred to as excessive or loud. Now, sound levels are expressed in units of decibels, which you may or may not have heard before. But it's important to remember that they're given on a logarithmic scale. Now, that really just is to say that if you're working or you're kind of referencing decibels, they don't work, or they don't kind of add or subtract arithmetically as you would typically think. So for instance, let's say you have two sound sources, 50 decibels and 50 decibels. If you were to add them together, typically you'd expect it, okay, well, 50 plus 50, it's going to be 100 decibels. But because the decibels are on a logarithmic scale, in fact, that's not the case. It would actually be 50 decibels plus 50 decibels equals 53 decibels. So it's not necessarily as intuitive, but that is because of the logarithmic nature of those units. And most often, what we're used to seeing is decibels expressed as A-weighted decibels. And that's because, especially in regulations and things like that, they're really attuned to how humans hear. So when we're assessing potential impacts on humans, well, we want to use the A-weighted scale. Now, that's not to say that there are other weightings, such as C weighting and unweighted decibels, as well as other weightings that can be used. But most often, we see A-weighted decibels. Further, sound can be reported on both a broadband or by octave band frequency. And, what is that? Well, broadband sound levels would be, for instance, kind of a single sound level, which is composed of a full spectrum of octave band sound level frequencies. So broadband level would be like 45 decibels. However, it's composed of a full octave band frequency spectrum. So it's kind of composed of those octave band frequency levels. Next slide. Now, when analyzing sound sources, these two terms are commonly used, the sound power level and sound pressure level. Sound power level is kind of a measure of acoustic energy that is emitted from a source and can't be measured. It's kind of inherent to the source, if you will. Whereas a sound pressure level is a measure of sound given at a receiver location, whether that receiver is a microphone or something else, or it can be calculated using information about the sound source as well as the surrounding environment. Sometimes an example I give to express this is the light bulb example. So the light bulbs usually have a wattage associated with them. Let's say a 60-watt light bulb. Well, the 60 watt is the power required to light the bulb. It's kind of inherent to the bulb. And then so that is the quote unquote sound power. But then the light bulb produces brightness, and that could be thought of as the sound pressure. So hopefully that's helpful in understanding a bit between these two common terms. Next slide. Sound metrics that are also used to characterize the sound power and sound pressure. I just kind of decided to include a few of the most common ones here. The first one being the equivalent sound level, or LEQ. So the equivalent sound level is it's essentially an average sound level. It's the average A-weighted sound level that's averaged over a specified period of time. And that's somewhat depicted here in the schematic on the right. But for all intents and purposes, it's essentially somewhat of an average sound level. Now the LN is the statistical sound level. The N refers to that statistical percent. So for instance, the N really represents the N% of time that it is exceeded. So for an L90, it means the sound level is exceeded the 90% of the time, or the majority of the time, really. So that might represent the lower background or residual sound level. Whereas if you were looking at an L10, that would be kind of, not the majority of the sound level, only 10% of the time. So it might represent transient sound sources. Finally, we have the Lmax, and that basically is the maximum instantaneous sound pressure level over a given measurement period. Now, you probably won't see that one as commonly, but certainly with respect to construction equipment, you may see that come up. Okay, next slide. So noise regulations, it's really important to research what regulations are applicable to your project. And noise regulations can be presented in a number of different ways, including in a qualitative and quantitative manner. So, when I say qualitative, it could be just kind of like a nuisance noise ordinance, such as, don't produce excessive noise during nighttime hours. There's nothing quantitative included in that statement. However, there can also be quantitative sound levels, and those are usually represented either as absolute limits or relative limits. Absolute limits are a specific decibel level not to be exceeded at a point of compliance, which point of compliance could be anything from a property line, a facility property line, to a noise sensitive receptor such as a residence. And an example of an absolute limit would be something like 50 decibels or 45 decibels. Now, a relative limit really allows for an incremental increase in decibel level over existing sound levels, so existing pre-construction sound levels. So that means that really we have to establish existing sound levels in order to adhere or demonstrate compliance with that relative limit. So that kind of requires us to establish existing sound levels through a baseline survey or other means. Next slide. So just to make things even more complicated, of course, we have to look at the regulations themselves. But in addition to that, we also have to, kind of see what has been done before. What is the past precedent that has been kind of made in this particular jurisdictions. Usually when I go to, I don't not only review regulations, I also look to see, okay, what if some successfully permitted acoustic assessments, what kind of information have they presented? What are the agencies likely expecting to see in this acoustic assessment and to satisfy them? Of course, it's ideal if you're able to actually consult with the agencies and ask these questions specifically, but sometimes that's not always an option, depending on the situation. So in any case, it's important to not only look at the regulations, but also what has been done for other previous successful acoustic assessments used for permitting. Next slide. So New York, New York, I've conducted numerous acoustic assessments in New York, and I will say it's very complex. It's a very rigorous and comprehensive place to have to permit something from a noise perspective, as they have state requirements, county requirements, and things at the local level as well, most often. So just to provide some examples, at the state level, the New York State Department of Environmental Conservation have a noise policy, which they call Assessing and Mitigating Noise Impacts. And they allow for a 6 dBA incremental increase criterion. Now, I've also seen the New York State Department of Public Service, or DPS, provide a recommendations document applicable to things like substations or converter stations. And that provides absolute sound levels that are applicable at points of compliance like the facility property line and off-site noise sensitive receptors. Now, not only that, if you're looking at New York City, it's very complicated as well. They have in the city level, they have regulations, they have their own noise code, as well as a zoning resolution. And those include absolute octave band sound frequency limits that are applicable at the facility property boundary and at offsite noise sensitive receptors. So, very complicated, and kind of require comprehensive review process. And not to mention, you have to make sure to cover other jurisdictions, because certainly in New York City, I've even had requirements at, in villages and other smaller jurisdictions that, may not really occur to you initially. So it's very important to do your research in New York. Next slide. So what project activities do we look at for in-air acoustic assessments for offshore wind? Well, we look at construction and operation. And for construction, we look at horizontal directional drilling, or HDD, impact and vibratory pile driving, helicopters, which may be used for construction as well, support vessels, and general construction activities. For operation, of course, we look at operation of onshore substations or converter stations, the operations of the offshore wind turbines or substations, and sound signals or foghorns. Next slide. Qualitative versus quantitative. Well, a lot of this has to do with the stage of design at the time of the COP submittal. At the time of the COP submittal, sometimes all of these details of the project activities may not be known. And so, that may drive some things to be addressed, at least at the time of the COP, in somewhat of a qualitative manner, while others are evaluated quantitatively. However, it could also be kind of driven by other things, such as, for instance, for qualitative, depending on maybe the distance of, the wind turbines or offshore substations from the shoreline, the distance is so substantial that perhaps we deal with it in a qualitative way. Same for the sound signals or foghorns, and general construction as well, not due to the separation distance, but for other reasons, we may deal with that in a qualitative manner, and I'll get to that later on. For quantitative, we certainly look at HDD, pile driving, and of course, onshore substation and converter station operation. Next slide. So this slide just kind of provides an overview of the acoustic assessment process. So first and foremost, really, we want to make sure that we gather the project information. And this is inclusive of the regulatory information as well. It's really important to establish, accurate project details and do that regulatory research at the beginning, so that, you can kind of set yourself up to do, an accurate assessment. Next, you want to organize GIS data. Geographic data such as terrain data, so that, again, you can build your model and, apply as much site-specific information as possible. Then, we want to, we'll need to conduct field work if it's needed, so ambient sound surveys. We proceed with the desktop acoustic modeling analysis, which, from there, we make our compliance evaluation. And then, depending on the results of the compliance evaluation, we can review noise mitigation if it's needed. Now, I should mention, prior to finalizing the acoustic assessment, sometimes it can be quite an iterative process. It may not just be one iteration, you successfully comply. That's ideal. But, sometimes tweaks need to be made. Sometimes site layout changes are made. And, so we conduct iterations as needed in order to, attain compliance, and then we hopefully go on to finalize the acoustic assessment. Next slide. So ambient sound surveys. So in New York, ambient sound surveys are usually required to document the pre-construction acoustic environment. And depending on the requirements or the guidance you might receive from agencies, you might be able to conduct short-term, so like less than 24 hours, or long-term, greater than 24-hour measurements. These measurements are usually conducted in the vicinity of the noise sensitive receptors closest to the project facility you're looking at. I mean, ideally, you would be on noise sensitive receptor property. However, depending on access, sometimes we also just have to collect measurements at publicly accessible locations as close to noise sensitive receptors as possible. And our measurements very much follow ANSI standards. So, we use, a type 1 sound level meter, kind of like the one shown here. We generally use Larson-Davis sound level meters, although there's other ones that can be used, of course. And we, position it in such a way to follow the standards and use a windscreen to make sure that it's shielded from wind interference, and of course, calibrate it properly in the field. Next slide. So with ambient sound surveys, each sound level is usually programmed to measure and log continuously a whole variety of A-weighted and perhaps, different weighting sound levels for the set interval that, the programmer determines. So maybe every second, every minute, every 10 minutes, every hour. And we typically collect a variety of metrics like the LEQ, like the statistical levels I mentioned earlier, as well as, full and third octave band sound frequencies as well. And upon the completion of the survey, we download the data, of course, for analysis, and we can extract extraneous data, let's say if it's due to precipitation or other intrusive sound sources from the data set, so that it doesn't interfere with the results of the survey. Next slide. So modeling. Modeling, we usually use Data Acoustics CADNA program. There are other programs that can be used, but certainly CADNA is well recognized and by regulators and by acousticians. And it conforms to the International Organization for Standardization, or ISO 9613-2 standard, attenuation of sound during propagation outdoors. And the algorithms within the standard affect how sound propagates and attenuates by incorporating all sorts of different factors, such as atmospheric absorption, ground effects, source directivity, meteorological conditions, heights of sources and receptors, and more. Next slide. So in acoustic modeling, we really do try to make it as site specific to the project as possible. So in doing that, we typically include terrain data, and the ISO 9613 standard also accounts for ground absorption rates by assigning numerical coefficients or ground absorption coefficients that range from 0 to 1. 0 being for acoustically hard reflective surfaces, and ranging from all the way to 1 for absorptive surfaces. So if the ground is hard packed, or of course, for offshore wind, for water bodies, the ground absorption coefficient that we would assume is 0. So it reduces, so it's considered perfectly reflective, and certainly does not aid in, kind of enhances sound propagation. It certainly doesn't hinder it, doesn't absorb it in any way. Now, in contrast, ground covered by, lush fields, agricultural land, that kind of thing could be, you could use a ground absorption coefficient of 1. Now for modeling, and it's generally a good engineering practice to use a semi-reflective ground absorption factor of 0.5, which we usually use, except for areas where the ground absorption factor is considered less than 0.5, such as water bodies or pavement, which we would use a factor of 0. Next slide. In addition, acoustic modeling, and it assumes a number of conservative assumptions, including first and foremost, so the ISO 9613 standard, it assumes what they refer to as omnidirectional downwind sound propagation. And so what that means is, let's say you have a sound source and then a receiver, like a residence. If the wind is blowing from the sound source to the residence, the residence is considered downwind. And that really affects and kind of, it encourages sound propagation. It allows for maximum sound propagation conditions. However, of course, wind can only blow in one direction at any given time. Well, that's not what the standard kind of assumes and the modeling assumes. It assumes that all receptors are downwind of all sound sources simultaneously. So of course that's physically impossible because it assumes that the wind is in all directions at any given time. In addition, the model assumes that we have laminar meteorological conditions. So there's no turbulent eddies, there's no change in wind speed or direction, nothing that can interfere with sound propagation. So that also kind of aids in kind of allowing for that conservatism. And most often, although it depends on the project, of course, and how the facility will be run, we assume that all sound sources are operating at full load simultaneously. And sound attenuation through foliage and offsite anthropogenic structures, buildings like apartment buildings or what have you, is ignored. So, those buildings may provide shielding and attenuation for sound, but we don't account for that. And I will say, I feel very good about the way that we model noise. I've had an opportunity to do a lot of acoustic assessments and a lot of operational sound surveys, and have found that the way we model noise compares well with those operational sound survey measurements. So, feel that we model in a way that is effective. Next slide. So HDD, horizontal directional drilling. Now, certainly I'm not an HDD contractor, but this is something that we look at for offshore wind acoustic assessments. And, they do produce elevated sound levels. That's really why. It's a trenchless construction method. And really, it's my understanding that really it's used to basically avoid features, whether it's like a water body, they want to avoid wetlands or perhaps something else on land. And the technique so they basically go underground underneath such features. The technique involves drilling what they call a pilot hole with the desired trajectory. They kind of enlarge that hole, and then that allows a cable to be pulled through it. So most often you'll see HDD used places like at landings, the cable landings, or perhaps onshore. Next slide. And this image here kind of shows an example of what an HDD might look like. This is just, of course, an example. They may look different from this, but just to give you an idea. And next slide. And so HDD, basically, we look at equipment that could be at the HDD landing, entry, or exit points. Because the sound emissions can vary due to the equipment needed at the exit or entrance. And this table here provides an example of sound power levels for HDD equipment. Now, as I say, these are just examples, and the sound power levels of equipment may vary depending on the models of equipment and the project details. So these are just examples. And really, HDD is kind of special relative to some other construction activities because, of course, with a lot of construction activities, if limited during daytime, a lot of times can be exempt from noise regulations. However, it's my understanding that HDD sometimes has to go past typical daytime hours due to safety reasons or other reasons. So, we do our best to restrict construction activities like HDD to daytime hours, but that may not always be possible. However, in the event that noise mitigation is needed, there are options such as acoustic enclosures or barriers, or perhaps exhaust silencers for certain equipment. Next slide. So next we'll talk about impact and vibratory pile driving. Pile driving can be used for a variety of activities for offshore wind assessments, including offshore foundation installation, cofferdam installation, substation construction, and onshore cable routing. And similar to HDD, which can generate elevated sound levels, so can pile driving. And of course, the sound levels can vary based on the manufacturer and model. But here, some examples of these are, for vibratory maybe a 127 dBA level, or impact maybe up to 137. But as I say, this could vary depending on the project specifics. So these are just given as examples. Next slide. So as I mentioned prior, like other construction activities, if pile driving is limited to daytime hours, it's often exempt from noise regulations. But you always have to review your site-specific noise regulations and requirements. For instance, in New York City, under their code, New York City Control Code, they impose specific limits on construction activities, including pile driving, such as a not to exceed 85 dBA at 50 feet at a point outside the property line. And for impulsive sound like pile driving, they even have a 15 dBA incremental increase limit relative to ambient for pile driving, and that's a very stringent limit. Just goes to show again that New York and New York City have a very comprehensive review process. Next slide. Moving on from construction to operation, of course, we look at the operation of onshore substations or converter stations. Now, an electrical substation is basically a facility that's a junction between electricity generation and distribution. These are onshore, so they're important to they're important sources to review, as they may be near communities and potential noise sensitive receptors. And being that their operational sound sources are considered permanent or semi-permanent, so we do model these. And they can include a wide variety of on-site sound sources, but some of them might include transformers, shunt reactors, harmonic filters, capacitor banks, coolers, or building exhausts or air handling units. But as I say, there could be other sources as well that I haven't listed here. The next slide. So transformers, they're really the main sound source when you're looking at a substation or converter station. There are three main sources of sound associated with a transformer: core noise, load noise, and noise generated by their cooling equipment or fans. Sometimes if you might see information about transformers, you may see a three-phase transformer, and that typically represents sound levels that are associated with no fan cooling, and then two different levels of sound generated by cooling with fans. Now, the core vibrational noise is really the principal noise source, but it doesn't vary with electrical load. The noise produced by substation transformers is really caused by the load current in the transformer's coils, and that's really attributed to the main frequency of the sound is twice the supply frequency. You're kind of used to hearing maybe that humming noise, and that usually consists of tonal components. And they're generated at harmonics of about 120 hertz. Next slide. Now, this image here just kind of shows an idea of what a schematic of kind of what a transformer looks like. But really, in order to understand and characterize sound emissions from transformers, the information that's pretty critical to us is, of course, the number of transformers on site. But also the dimensions of transformers, the megavolt ampere rating or MVA rating, and the NEMA rating, which is kind of a standardized rating for sound levels of transformers. And of course, if available and applicable, sound specifications for that transformer or field test report from the manufacturer. However, it's recognized that sometimes, depending on the stage of design, all of those details may not be available, especially the sound specifications. So in the past, we've seen DPS allow for development of the sound profile using the electric power plant environmental noise guide calculation methodology in order to determine the sound emissions from the transformers. Next slide. And this slide here really just gives another idea of kind of the sound power levels you could see from different on-site sound sources. However, again, this can be variable and change depending on the specific project you're looking at. Next slide. As I've kind of conveyed, we use CADNA to produce our acoustic models for for our offshore in-air acoustic assessments. And we really tried to build the facilities in 3 dimensions, which is kind of what's shown here. This is basically a snapshot from the model and shows how we can build structures and then assign the sound sources to those structures, as well as include the offsite receptors within the model itself. And you can kind of go in there and see how it looks in 3 dimensions. Next slide. And in terms of results, once we model, we usually produce a couple different types of results. We produce predicted sound levels as discrete sound levels at offsite noise sensitive receptors like residences, schools, hospitals, whatever ones are nearby. And then oftentimes we also produce what's shown here, which is a sound contour plot, and basically shows how the sound is distributed throughout the project area. So these sound contours, they can kind of be analogous to, if you know, like terrain contour data and things like that. It basically shows how the sound dissipates from the sound source to the receivers. Next slide. So once we have modeled the sounds, the substation or converter station, we assess compliance relative to the noise regulations we're looking at. And at the points of compliance, whether it be the residences or property lines or what have you. In the event that we do have exceedances, we're able to review potential noise mitigation measures, which could include things like modifications to site layout design, selection of low noise equipment, noise barriers, enclosures, silencers, or perhaps addition of absorptive materials. Next slide. So that kind of concludes most often the activities we look at from a quantitative perspective. Now for qualitative, a lot of times we choose to look at general construction this way. And when I say general construction, that includes installation of onshore export cables, other onshore infrastructure, whether it's the substation or interconnection cables. And the reason really for this is why we kind of deal with it in this qualitative way is because noise levels from construction activities like these can vary tremendously depending on so many factors, like the types of equipment operating at any given time, the number of equipment, the specific equipment model, the operations being performed, the condition of the equipment. They're always moving, and it's a little bit harder to quantify than a stationary sound source like a pile driver or HDD. And we look to oftentimes the US EPA or the Federal Highway Administration to obtain sound information to characterize those general construction equipment. Next slide. In addition, support vessels, oftentimes we deal with in a qualitative manner as well. Vessels will be used to transport crews, materials to the offshore lease area, perhaps to also work with the export cables and the inter-array cables. And really, the International Maritime Organization has established noise limit for vessels, although those are mainly applicable to external areas to the vessel itself, including a 75 dBA limit to external areas on those vessels. Really near shore at the shoreline receptors, generally they won't be exposed to noise levels from those vessels for any extended period of time. Next slide. Now, helicopters may also be used for maybe accessing or inspecting wind turbines or for emergency operations, or maybe transferring crew. Usually the helicopter route plan is developed to meet industry guidelines, and best practices are used according to FAA guidance. These types of helicopters generate a whole slew, kind of a whole gamut of different sounds related to the rotor, as well as aerodynamic sound. So it's generated by a number of sound sources, and we usually deal with this as a qualitative as well because it is considered temporary and a short-term sound source. Next slide. So of course, offshore wind turbine operation. Well, wind turbines in comparison to other conventional energy facilities are unique because as sound is generated from the wind turbine will increase as the wind speed increases. The wind turbine sound is usually negligible when at rest, but increases as the rotor tip speed increases and then is constant once the maximum rated sound power or maximum rotational wind speed is achieved. So other sound sources, of course, are not affected by wind speed, but wind turbines are, and so they're kind of different that way. But it's also important to recognize as wind speed increases, the background ambient sound level will also increase, and this results in masking effects. So really the net result is that when there's elevated wind turbine sound emissions occurring, the sound produced by other sound sources, let's say from foliage or from waves crashing at the shoreline, will also increase. So in practical terms, this means that a nearby receptor like a residence may hear those other sound sources like the waves or foliage or similar, rather than actually sound from the turbine. Next slide. And not only are offshore wind facilities unique because of kind of the wind factor, but also because they're surrounded by water, which, as I mentioned earlier, is perfectly reflective. It's really different. Sound propagation is really different from offshore turbines as opposed to land-based turbine because it involves this completely reflective surface surrounding it. Sound propagation over water is variable and depends on a number of factors, like the distance from the water to the shoreline receivers, the height of the wind turbines themselves, the meteorological conditions, and as well as the attenuation from the ground when it hits the shoreline. Next slide. Also, sound signals or foghorns are sometimes installed on select wind turbines at the outer perimeter of the lease area. However, again, due to the large separation distance, sometimes like the wind turbines, the sound level is typically below what one can hear, although this certainly depends on the distance from the shoreline to the project. Next slide. So some final thoughts. Hopefully I've made it pretty clear that it's very important to conduct a comprehensive review of noise regulations and requirements to make sure all your bases are covered. Also, if possible, it's great to be able to reach out to the regulatory agencies, for further guidance. If you have questions, if that's possible, certainly that's a preferred way to go. And of course, we have to make sure to identify all the project-related sound sources and activities. I know certainly in this presentation, I mentioned that some might be dealt with qualitatively versus others quantitatively, but that really depends from project to project. That may differ. And in addition, it's important to take time to organize the site-specific inputs and assumptions. This means working alongside the offshore developers very closely to make sure that we can model the project as accurately as possible, so that our compliance assessments, they're meaningful. Next slide. Of course, the goal is always to successfully demonstrate compliance with the regulations and requirements. And this may occur in time for the COP submittal, or it might occur potentially closer to pre-construction. However, as I've stated before, New York is very comprehensive. They're very stringent in attaining, making sure that compliance is shown. So in the event that compliance is not successfully demonstrated in time for COP submittal, typically further modeling may be needed, down the road so that they can demonstrate compliance. Now, we have seen some instances, especially with construction activities like pile driving in the city of New York, where you may, the Public Service Commission may provide some waivers. However, that's kind of on a project by project basis. And certainly the operational sound sources are not typically subject to such waivers. Next slide. Well, I guess that closes my presentation. Thank you so much for listening, and hopefully you found this informative. And please let me know if you have any questions.
Thank you so much, Tricia. That was a very interesting presentation, and I think that's something that folks think about a lot with these projects. The impacts during operation, and once they're built, how we come about the permitting and regulations for these things. So I found this particularly interesting. So thank you so much. A quick reminder to the audience to please use the Q&A function to submit your questions for Tricia. Please use again that all panelists drop down if you see in the Q&A tab to ensure that the NYSERDA team receives your question. If you send it privately, sometimes we don't see it and then your question does not get addressed. So while folks are perhaps finding that Q&A tab, Tricia, we have a few questions that came in. So I wanted to pick up where you sort of left off with one of your final thoughts about the changes that can happen between the COP approval and perhaps when pre-construction starts. So what happens if a substation site layout changes after the assessments are done and the recordings, the data is gotten in the field? How does all of that change after the approvals of the COP submittal?
Well, yeah, certainly in my experience, I've seen that the need to adhere to the regulations and to seek approvals doesn't end with the COP. There's other layers of regulations. Sometimes, for instance, Article 7, or kind of dependent on the process that you're going through. The need to kind of further analyze and kind of successfully demonstrate compliance with whatever layout and equipment has kind of been determined even post-COP. So kind of making sure that we're looking at what's actually planning to be installed and ensure that that is a compliant layout and kind of equipment selection.
Great, thanks so much. Do you decide, or not you, but does a consultant or whomever is getting those recordings, those readings, how do you decide where the ambient sound measurements are conducted?
Yeah, that's a good question. Yeah, most often, so for offshore wind, typically, although these things can always vary. However, typically we found that ambient sound measurements are commonly required near the HDD exit and entry points, as well as near onshore substation or converter stations. And as far as where the ambient sound measurements are taken, we usually try to position them at locations coincident with the closest noise sensitive receptors in each geographical direction. So basically trying to capture the existing pre-construction ambient sound levels near those closest noise sensitive receptors. And so we would do that for, let's say, the onshore substations or converter stations or HDD locations as well.
That's great, thank you. In this presentation, in this conversation, I'm hearing a lot about human impact and the onshore recordings. What about, which are incredibly important, what are the in-air noise limits for protected species above water surface, offshore and onshore? So I think that this person who asked this question is interested in perhaps wildlife that might be offshore or even onshore for that matter, next to rookeries or nesting areas for birds, seals, sea turtles, etc. So I think the question is, are there limits for those protected species?
That's a really good question, and not an easy question to answer, because I'll admit, actually, for the most part, a lot of regulations and criteria they're very much set for human receptors. We know we have very set guidance now for marine species, and those do include sea turtles. But as for other wildlife and birds, so for like terrestrial wildlife, I should say, it's not as well defined. So it really requires a lot of research into sometimes the specific wildlife creature that you might be looking at. I have had to do some research into criteria for birds in the past, and that kind of is more on a broad basis as well. I've had to look at really specific ones, like, now this wasn't for an offshore project, but for sage grouse, for instance. And actually, in my experience, the sensitivity, at least that I found for when I did that particular research, is that birds actually those specific birds at least were found to have sensitivities very similar to those for humans. However, as far as other specific animals you may be looking at, I can't say that I have just specific limit I can share with you all right now, because many of them are kind of under development or require a bit of research because it's such a specific kind of such a specific question. Every kind of creature can be different, and for whatever reason, it's just not as well defined area. I'm not saying that it shouldn't be, but it's not as well defined an area for noise as human and marine species are. I'm not certain why, but that's the case. So I'm sorry, I'm probably not maybe the most thorough answer you'd be hoping for, but that's kind of reality right now.
It also sounds like if there was a need to come, to find that limit, there would be research done if you were hired by a developer or whatever to try to, discover what that might be or note that there's not a limitation, that kind of thing. I think it sounds like it would be comprehensive and at least attempting to figure out what that limitation would be.
Yes. Oh, certainly. You're exactly right. You put it so perfectly. Yes, exactly. It's such a case by case basis that yes, it would basically be kind of yeah. If a particular protected species was of concern for a project, we would obviously really research that and come up with a strategy for assessing that in our acoustic assessment as well.
Great, thanks so much. So the question came in that I think is of interest to a lot of folks. How high is the noise level for an onshore substation for offshore wind compared to a normal power plant? Are they different? Are we talking about because it's a different, energy resource or type, maybe even different technologies or transformers for that matter? Is there a difference in those numbers or those limits for those two different types of power plants?
Oh, for the limits.
How high is the
Well,
noise level? So I think
oh,
that,
hi. Okay,
limit.
yes.
Mhm.
Well, in general, if you're speaking on power plants, I would say that substations would generally be lower level noise than power plants. Actually, I have analyzed many power plants, and usually they are a lot more complex as far as they have huge turbines, compressors, big air filters. They have transformers themselves, so even sometimes they have their own substation on site at a number of power plants. So they they really aren't comparable. At least in my experience, they're not comparable sound sources. Substations or converter stations would be, typically a lot smaller footprint and a lot less sound sources relative to your typical power plant.
Great. Thanks so much. Okay, so getting back to some of the regulations and whether they're not complete or up to date, this person with this question says that the in-air acoustics assessment impacts are important factors. However, regulations might not be up to date. So while these impacts will affect the larger community, how does OSHA apply to this or anything similar? So it sounds like what other factors can play in if there isn't like a limit or some of those factors aren't well known.
No, that's another good question. And I will say that while actually our group does look at some OSHA related requirements, OSHA really pertains and OSHA guidelines and noise requirements are, federal requirements and really apply to potential receptors. So really workers, or I should, workers on site at facilities like substations. So I will say generally and especially for COP related in-air acoustic assessments, we're really focused on off-site noise sensitive receptors, houses, hospitals, schools, beyond, the boundaries of the project to make sure they're adhering to regulations. It's not typically within our scope to look at the impacts to workers. However, that's not to say it's not important. And that is something that is usually looked at separately as part of another assessment and something that the developer kind of has to make sure that either the sound levels on site are in accordance with those OSHA guidelines, and that if needed, workers are equipped with proper protective equipment, like let's say if they would need ear like kind of ear muffs, that's not to say that they're required, but if they may be required, they equip them properly with that type of protective equipment. But those certainly do have their own guidelines that are important, but not really within the scope of the COP or the general community. That is really specific to folks that are working on the project. Yeah.
Great. Thanks so much. Appreciate that. This person has a question specifically about New York State requirements. I know you had a slide on that, and you touched a few of those. So perhaps maybe referencing that information, can you please share what specific regulatory requirements exist and must be complied with? And this is in regards to New York, is what the person said. So I'm assuming the state.
Okay. Well, it does depend from project to project. As I did state in the presentation, most often we do look at the Department of Environmental Conservation, that 6 dBA incremental increase, so 6 dBA over ambient. And then if you're looking at, now this is really pertaining to substations or converter stations, not necessarily to other sound sources, but there are those recommendations that DPS has issued. And those have limits that are, I'm trying to remember, I believe it is, hoping I'm remembering these right, 45 decibels, I believe, at the facility property line, and 35, I believe, at offsite noise sensitive receptors. Those account for, also, I should mention that those limits account for tonal penalties. So, which a tonal penalty, some on-site sound sources at facilities like substations, like the transformers, can be considered tonal. So they kind of have, it's basically related to the sound levels that they're generating at certain frequencies. So if sound levels can be tonal, which transformers sometimes can be, as well as other on-site sound sources, if there's the potential for that, you have to take a 5 dBA penalty. So when I'm stating the limits that I mentioned before, those account for that penalty. And I should say those DPS recommendations are very, they are very stringent. I mean, a 35 dBA level, especially, depending on the location, could be similar to ambient or below ambient conditions. Now that is very much, depends from site to site. So as far as other New York requirements, those are the most typical at the state level. But of course, as I mentioned before, there can be all sorts of different further limits and restrictions at county or town or city levels, things like that too.
Right, great, thank you. And probably for the person interested in looking this up, I did see that you cited not only DPS, but also DEC, the Department of Environmental Conservation. So perhaps some more information can be found with those agencies. Great. I think we have one last question for you. This person is interested, when and how are noise and vibration criteria set in the acoustic assessment process? This is more of a process question.
When are the criteria set?
When and how are noise and vibration criteria set?
Well, they have to really be when. The answer to when is really, that's kind of almost the first and foremost. Oftentimes I really try to even do that research at the proposal stage. So before we win a project, because we need to know what kind of scope will the project require. Do we need to conduct an ambient sound survey? If so, that should be included in the proposal. Now, usually if we win a project, we go on to even investigate those regulations further. But as I say, I mean, determining when you have to figure out those is really at the very outset, to kind of be able to help to work alongside the developer to assist in, siting and other kind of decision making. And then as far as where?
When and how?
Oh, when and how. How? I mean, I really will say, I've researched a lot of regulations in my time. So I guess I kind of know where to look and how to look for them. It is really, in all honesty, a lot of online research. You can also look at other permitting documents if you're uncertain, or maybe pose questions. Like I have called counties before to ask them questions about noise requirements, if it's because sometimes they're not published online, and so I want to confirm that okay, there's no requirements perhaps, or something like that. But really it is a lot of times online based.
Great. Wonderful. Well, thank you so much. We are at the top of our hour, so we appreciate everyone listening and tuning in this afternoon. Thank you so much for joining us for this Learning from the Experts webinar. A reminder that the webinar recording and presentation slides will be available on NYSERDA's website. Our next webinar in the series will be March 20th about how converter stations how converter stations and substations support offshore wind. So sounds like a good next step from this presentation. You can register for future webinars through our events page at wind.ny.gov. We also encourage you to check out past webinars in the series on NYSERDA's website and YouTube channel. Just reminding everyone, this is our 40th, so 40th webinar. So there are a lot of wonderful topics online for you to view. If you have requests for future topics or you would like to hear about in this series, please email us at offshorewind@nyserda.ny.gov or fill out our Learning from the Experts survey posted on the website. Thank you so much, Tricia, and thank you to the audience for joining us today. See you next time.